Okay, so in this video we're going to look at the case of when a moving charged particle enters an electric field, and specifically at right angles to that field. In other words, this situation. So we've got two electrodes, parallel plates, creating an electric field, and in comes a particle, a charged particle. And basically we want to sort of establish what would happen to the charged particle. In other words, how much would it be deflected by the field? So, well, let's first of all put in a few bits of information. Let's decide what our particle is. So, well, supposing our particle was a proton. So let's have a proton. And let's suppose it was approaching the field with a velocity of 7.8 times 10 to the 5 meters per second. So, and it's kind of heading in horizontally. Well, it's a proton, so therefore we know, don't we? We know its charge. We know the charge will be E, the charge on a proton, 1.6 times 10 to the minus 19 coulombs. We also know the mass of a proton, don't we? The mass of a proton we can look up, and it's 1.67 times 10 to the minus 27 kilograms. So I'll just put that data up there because that's going to be useful. Well, other things that we will need to know are things like, for example, the potential difference between the electrodes, because we haven't yet decided what that is. So let's supposing the top electrode or metal plate is at 1000 volts and the bottom electrode is at 0. So we've got a potential difference of 1000 volts there. Well, that of course tells us the direction of the electric field. It's going to be going from positive to negative. The direction of positive charge will move when in the field. So we can start to see what's going to happen to the proton here. Well, other information that we'd probably be given in a question is, for example, the separation of the plates, because we're likely to need to work out the electric field. So, well, let's see, that would be this distance here. And so let's put in a separation there. And let's suppose we've got, let's suppose it's a gap of 40 centimetres. Let's suppose D, yes, is 40 centimetre separation. We're also going to need to think about kind of how long this proton is between the plates. We know how fast it's going. So that means that it's going to be useful to know the plates, how long the plates are, so that we can kind of figure out how much time is going to be stuck between those plates. So let's put that distance in as well. Let's suppose we're told that, and let's suppose that's 50 centimetres, or half a metre, 0.5 metres. There we are. Brilliant. Okay. Well, that's looking quite interesting. Now the question would be quite specific, but generally we know that there's going to be some effect on the proton here as it enters the field. Let's have a closer look. Well, here it comes in to the field, and of course when it kind of zooms in, it's suddenly going to be acted upon by a vertical force. Horizontally, its velocity is not going to change because there's no horizontal force acting, but there is now suddenly going to be a vertical force. So, well, what will the effect be? Well, this might remind you of something here. So it's going to start to accelerate downwards because of the vertical force. Of course, it's still got the same horizontal velocity, no change, but now it's going to have a vertical downward velocity because it's been accelerated somewhat. This will hopefully be reminding you of projectiles. Let's see what the next stage might be. Well, again, the horizontal velocity unchanged, but now going even faster vertically because it spent more time being accelerated by this vertical force. And eventually this proton is going to leave the electric field and zoom on its way, and then again it will cease to be acted on now by the vertical force. Well, yeah, this is, like I said, a bit like a projectile. We're going to get some kind of parabolic path, or specifically a parabolic path while it's inside the field. We could just remind ourselves quickly about a projectile in a gravitational field, because that's what we're more familiar with. And yeah, you'll remember that when you have that situation, well, it's exactly the same actually, because you've got the ball being projected horizontally off a cliff, and absolutely what happens is, you know, the horizontal velocity doesn't change, but it's accelerating under gravity. And so for that reason, you know, you get a bigger and bigger vertical velocity. And we know, don't we, how to deal with that, hopefully, if your year 12 projectiles stuff is good. So we can figure out all the mathematics of what's going on there. Well, we're going to apply the same mathematics now to what is effectively a projectile of a particle in an electric field, but not under gravity. So we'll get rid of that one because that's in the way, I need that space, and we'll analyse what's going on. And our objective is specifically to find out what will be the vertical displacement of this particle, of this proton, by the time it exits our field. So in other words, what I'm looking for is, as it emerges from the field, what will be this vertical displacement of the particle? What distance will it have been moved through the field? Let's call it y, during its journey through. Right, so it looks like quite a complicated thing, so we're going to break it down step by step. So first up, well, proton zooms into the field, and once it's in the field, we want to know what the force will be on it. So first we need the electric field strength. So let's do that right straight off. So the electric field strength, well, it's a uniform field, and hopefully you'll remember that it's V over D. And by the way, I mean, if you want to pause and see if you can find Y, feel free to do so. That would be really good. So E is V over D, and we can calculate that will simply be 1,000 divided by 0.4. 40 centimetres means 0.4 metres. And if we evaluate that, we get 2,500 volts per metre. Next stage, let's determine then the force on our proton. Well, remember that E is F over Q. This is a really important equation. This is always true for electric field strength. So of course I can rearrange that, and I can say, well, if E is F over Q, then that means that F is E times Q. And so I can find the force on the proton. We know it's going to be downwards because the positive charge is going to be repelling away from the top plate. So it's going to be 2,500, and we've already remembered on the top left there that the charge on a proton is 1.6 times 10 to the minus 19 coulombs. Great stuff. So evaluating that, we get 4.0 times 10 to the minus 16 newtons. Not a very big force. But, of course, it's a very, very small particle, so we're now going to find the acceleration. Well, A is F over m, F equals ma, rearranged. So we just have to evaluate the force divided by the mass. And, of course, the mass of the proton is tiny, 1.67 times 10 to the minus 27. So what that means is that we get actually a huge acceleration, 2.4 times 10 to the 11 meters per second squared. Brilliant. So look, all of a sudden, we're actually in a powerful position. We now know the acceleration on the proton. 2.4 times 10 to the 11. Well, at this point, we can just say, well, what about gravity? Because we were talking about projectiles, and of course this is vertical, so there should also be gravity acting. This force is due to the electric field strength, the electric field. Well, correct, gravity will be acting on the proton, but of course at this moment we can just notice that gravity is going to be negligible. The acceleration due to gravity on Earth is about 10, isn't it? 9.81. Well, that's completely overshadowed here by this incredible acceleration of 2.4 times 10 to the 11. So we can forget gravity, basically. In other words, the time the proton spends between these plates, gravity is basically not going to have time to do to move it hardly at all, insignificantly compared to the effect of the electric field. Good, so we've got the acceleration. Now, how do we find y? Well, this is where we kind of go back to our mechanics. And of course, what we need to do is apply our old friends, the Suvat equations. So, and hopefully you're pretty good going. Another opportunity to pause and see if you could figure out the answer here. Okay, well, we're looking at, you always have to decide with Suvat equations which motion you're looking at. Well, we're here looking at the vertical motion. And so I'm going to write down SUVAT for that vertical motion that it's doing on its, from the equilibrium line or the centre line down through that displacement y. Well, we know that its vertical displacement is y, and that's what we want to find. What's its initial vertical velocity? Aha, well, it's moving horizontally, so its initial vertical velocity is 0 meters per second. Its final vertical velocity, we have no idea without calculating it. But we do know, of course, its acceleration. Its acceleration, we've just calculated 2.4 times 10 to the 11 meters per second squared. What about the time? Well, we don't know it, but can we work it out? Yes, we can, because we know that it's moving into the field with a horizontal velocity which doesn't change, 7.8 times 10 to the 5. And we know the distance that it's the length of the plates. So all we need to do is very simple. We can say, well, horizontally, in the horizontal motion, we know that the velocity will be the distance divided by the horizontal distance, let's call it x, not to confuse with the plate separation. So that's the horizontal distance x divided by the time taken. Rearrange, then we get that the time is x over v, which is 0.50 divided by 7.8 times 10 to the 5. And if we plug that in, then we get 6.4 times 10 to the minus 7 seconds. So you can see it's it's going so fast. It's only between the plates for a fraction of a moment, 640 nanoseconds, we could say. Well, great, that means that we've found the time, so I can actually write that in now. So I'm going to write that in there, and so there we go. So we've now got quite a whole load of information. And then we need to decide which Suvat equation to use. Well, we want y, so we've got to have s in our Suvat equation, and we must just make sure that we don't have an equation with v in, because we don't have any clue what v is. So we want an equation with s, it can have u, a, t, but not v. Well, we can pause there for a moment, and you might want to think of which one it is. Well, the equation to use here is s equals ut plus a half at squared. And the reason for that is because all the others have v in, so we can't use them. Well, we're now going to apply it. So we've got y equals 0, u is 0, so u times t is 0, plus a half times at squared. Great, let's plug in our data. Y equals a half times 2.4 times 10 to the 11 times 6.4 times 10 to the minus 7. That t is squared. Chuck it in the machine and let's see what comes out. Well, it comes out to be 0.049 meters, which is 4.9 centimeters. So fantastic. What we've done there is just to recap, just by knowing the field strength, we know the velocity of the particle coming in, by knowing the electric field strength, or at least calculating the electric field strength, We found the force on the particle, we found the acceleration on the particle, and then we've used SUVA, just like in projectiles, to find out the vertical displacement after a certain time. So it's powerful stuff, and it's a classic. Lots of questions use that idea in one way or another. After this video, there's a question to have a go at and see if you can apply these ideas.